Hi, welcome back to this video series on cryptography. Today I will talk about how we can make use of the index of coincidence metric that I introduced in my previous segment. Suppose you are given a string x, right? How do we define index of coincidence? It's nothing but I equal to 0 to 25 because we are working with the English alphabets, right? Alphabet letters A through Z. And we encode it. A means 0, B means 1, and Z means 25. Okay, pi square. Okay, I explained the reason for this formula in my previous segment, so please watch that. Pi stands for the probability. For example, when I is 0, P0 means what is the probability the letter is A? What is the probability the letter is B means P of 1? Okay, so P0 means probability that letter is A. Okay, we don't distinguish between small a and capital A, so that doesn't matter, right? So you're picking a letter, and what is the probability that letter is A? That's basically P of 0, and so on. So you probably know P of 25 is probability of Z occurring in that given string X. Okay, you can easily compute the probability, right? All you have to do is measure the frequency and divide it by the string length of the input X. Then you know how to find the probability. It turned out that for the English language, this is approximately equal to 0.06. This is a pretty interesting finding. Somebody has studied multiple magazines and articles, whatnot, and measured the distribution of probability of different texts, right? And found out that they can approximate it by 0.065. So this is going to really help us to break some crypto systems. Today I will first start with very basic ones like the Cipher, and I will show how we can break the Cipher using this notion of index of coincidence. Okay, the idea is pretty neat. The idea is that we will compute so-called index of coincidence by doing some pattern matching, and then if we find out something close to 0.05, we know we found the correct decryption without even having the key. Okay, so if you have to follow the remaining parts, I encourage you to watch the Cipher definition first, but I will quickly summarize what it is. So in the context of a Cipher, all we do is say we want to encrypt a message X, right? Made of, it's a string made of English alphabet A through Z, right? Alphabet letters. How do we encrypt? All we do is we encode X first by number. Every alphabet is mapped from 0 through 25 inclusive, A0, B1, and so on. Therefore, we can easily define encryption using a mod operator like this. You do X and K, right? K is your secret key. You do mod 26 because you don't want to go out of the set that you're working with, which is A through Z made of 26 letters. Okay. Of course, the key K has to be a number between 0 and 25. Okay. Similarly, you can define decryption very easily by taking your ciphertext Y, right? Let's call this as Y. How do I decrypt now? It's very simple. We will take the Y and we subtract by K, and we proved in the previous videos that this will give back the X. Okay, this is a simple concept, very nice concept, simple concept. In order to break this, there are a couple of ways to do it. One way is, so suppose you are given Y, you could try different K, right? From 0 all the way to 25 and keep calling the decryption function at most 26 times. And you will find out given X, if the X looks meaningful, okay, in quotes. So you will try K to be 0, you will try K to be 1, and look at the individual outputs one by one, and then see whether it makes sense. So let me show you that technique first very quickly. So I have already written the Cipher and the brute force attack that I just mentioned. So all I'm going to do is just take the simple string that I have for you, right? So this is a simple plain text string, if you want to call that way. And I'm going to call what I'm going to do is encryption using Cipher, right? Let's say I wanted to shift by 5 positions, okay? And now we can print the ciphertext. So it should hopefully look gibberish, which is good. But let's do we can also confirm that our algorithm works correctly by quickly decrypting it and doing the shift by 5 position back. Then we get back, this is not a random string. I want to demonstrate the value of IC. Is this the input that I have given? Of course, when you do Cipher's cipher, you usually remove spaces, dots, and so on. That's the reason why the decrypted text looks slightly unreadable, but you see it's the same as what the input was. But the question is, can we decrypt without knowing the key? That's where the fun part is, of course, from a cryptanalysis perspective. The answer is yes, and I will show you how to do that. So all I am going to do is basically call my brute force function, right, which will just simply try my ciphertext for multiple key values from 0 through 25. And let's scroll up to see the 6th row, because our key is set to 5. So we start with 0, 1, 2, 3, 4, and 5. That's perfectly fine because we got exactly what we needed. But you notice that I have to go through all of them one by one and to figure out, did I get the correct key? Okay, but it would be fun to automate this process. You may try to use dictionary, but then maybe by accident some of the strings of your output may be in the dictionary. Therefore, you're not really necessarily sure. Also, it becomes more complex because you're removing all your spaces and dots, so substring matching may not be perfect, right? So I suggest that we will make use of the index of coincidence to automate this process. Okay, so how can we do that? So let me go back to the index of coincidence discussion. So the idea is pretty neat. Let me create some space here. So what I'm going to do is I'm going to stare at this equation, right, IC of x, and tell you something about the behavior of IC of x, this equation that you're seeing here. Okay, what is this equation really? It's not really equation. This is a fact that was empirically obtained for English language, right? What if we take a plain text, okay, and rotate it by, say, or shift it using the shift cipher by 2 positions, for example? Will this equation still hold true? The value of ICX, what happens to the shifted value of ICX? Yeah, it may be tempting to say it will not hold true, but it is not correct. In fact, actually, even if you shift it by a few positions, your ICX value won't change, even though the ciphertext looks gibberish. So now let's go back and confirm that. What I'm going to do is I'm going to compute the IC of x, the index of coincidence, right? And I will compare how the ICX behaves. Okay, so let me compute this. I'll use the small IC to compute the plain text. I think I call it plain text or no, string. Okay, so what is my string? My string is this text. So I'm going to call this now, and I would like to be able to see the value of IC. Okay, it's 0.065, right? If you round it here, you get exactly 0.065, which is 6, which is very nice. But now let's do shift cipher. We already did that, so we have the ciphertext. So we can try the let me call it IC new, for example, IC shifted. Let's see what happens if I compute the IC of the ciphertext. Okay, it's also the same as the IC of the plain text. You may be wondering, why is this the case? Remember, ciphertext is basically obtained from the plain text by moving each letter a fixed amount of positions. So every A will be moved to, say, 5 positions. Mean where will A go? A will be transferred to B, C, D, E, F, G, for example. So you can see every letter is going to be transformed into another letter, transferred to another letter. But the number of times, if A occurred 10 times in the original text, the transformed A, the image of A, if you want to call that way, will say, for example, the image of A is say F. Okay, F will also occur 10 times. So that's how the shift cipher actually works. Therefore, the overall permutations preserve this property when you do sum of all the probability squares, right? Because instead of A occurring 5 times, you will have now a new constant F occurring 5 times. Okay, so the permutations, actually the probabilities are just permuted. Okay, that's basically what I wanted to tell you. Therefore, the effect of computing IC on the ciphertext has no new knowledge for us. It doesn't tell us anything about the plain text. Okay, so how do we now use IC then? So what I'm going to do is I'm going to argue like this. First, let me convince you that this is not only for one particular shift. We can do one more round of ciphertext if you prefer that way. So let's do. Let's compute by shifting it by 10 positions, right? Or even more easier if I just shift it by 1 position, because now we can see very easily how the ciphertext looks like. So A will become B, B becomes C, and so on. If you look at, say, for example, here in this original input string, where will I go? I will go to J. Okay, now let's count how many times I occurs here. 1, 2, 3, 4 times. Okay, what about J in the transformed one? 1, 2, 3, 4. That's it. So every letter gets transformed into another letter. Therefore, the frequencies are maintained. That's the reason why we get the same IC value. Now let's do the IC shifted, right, for the ciphertext, and convince ourselves that's the case. Yep, it's the same as the IC, the index of coincidence for the plain text. Amazing. So how do we now make use of this IC thing? So what I'm going to do is I'm going to go back to the whiteboard and do a small trick in the definition of IC of X. All I'm going to do is rewrite the IC of X as follows. We don't know, assume we don't know the plain text. We are given only the ciphertext, okay? But we are trying to guess the plain text from the ciphertext automatically, not manually browsing through all of the outputs, okay? So what if I rewrite this definition like this? Pi square means I can rewrite it as Pi times Pi, right? That's exactly the definition of Pi square, okay? I equal to 0 through 25. There's nothing new, right? It's just Pi square is expanded into Pi. But now let's take a look at Pi. So where will Pi go? Pi means the probability of the randomly chosen letter I. What is the probability that the randomly chosen letter is I, essentially, right? When I say I is a number from it could be 0, 1 through 25. Okay, that's basically what we are talking about, Pi. So remember from the demo we did, we know that the frequencies will be maintained when we do shift cipher, except that it gets rotated. Okay, so if a letter occurs 10 times, there must be another letter that also occurs 10 times in the transformed ciphertext. Okay, so what if our Pi, what if we treat it like this? Pi is same as Ui plus J. Ui is essentially the same as Pi in the sense that you're looking into the ciphertext and computing the frequency of each letters, okay, in the ciphertext, okay, as opposed to plain text. That's all. There's no difference other than that. So what is this J thing then? J is the amount of shift the plain text has gone through, but we don't know what J is, okay? We're trying to find the J. So how do we find that? So we are going to do this loop now. We are going to try to compute Pi Q I plus J, right? For, well, our I has to be from 0 to 25, that's for sure, because we have in English 26 letters. So we will try this. We don't know Pi, but we will be using the English language property about Pi. So I have shown you earlier the table of frequencies in English language. Therefore, we can find out P1 through P25. We're going to make a guess for J, starting from J to be 0 all the way to 25, right? These are the possible moves each letter can have. And for each such j, so I'm going to index it now. Okay, suppose you're given the ciphertext y. Y is the ciphertext we want to break. All we are going to do is we are going to compute this for different j, right? J can be 0, 1 through 25. As soon as we find a j such that IC of a j, IC of y at a particular index j is greater than or equal to say 0.064, then we know we found the right j. Okay, what does that mean? It means we found out how many steps or how many shift positions were used to transform our plain text into ciphertext. So that's basically it. So all we need to do is just look at this output and then confirm what is the j. So I will convince you this is going to work, and then I'll come back and explain more why is this technique will work. Okay, so let me show you that now. All I'm going to do is now call the brute force, but I will be passing just the ciphertext. Okay, right away we found out the value of IC is almost 0.065. Remember I said anything more than 0.064 should be considered, and there's only one key because we shifted it by only one position, so we right away get it. So let's do the same now on other shift positions. Let's shift the plain text by 5 positions, right? And let's do the brute force now. Are we going to get it? Yeah, you see here, we clearly got the key to be 5, and we got the plain text we wanted. That's really nice. That without looking into all the potential plain text manually, we can automate this process using this nice property of index of coincidence. So let me now explain to you why is this working actually. What is the reason behind it? So a couple of things. First, I will show you a brief demo of my source code. The idea is basically whatever I sketched on the whiteboard. Here is the English language distribution that is coming from analysis of large documents, a collection of documents, and they found out the probability for each of the English letters. Okay, if you choose a word, what is the probability the word has? Or if you choose a piece of text, not necessarily small word, but if you choose a piece of text, not so small, say it is made of 2-3 lines, right? Usual Word document, 3 lines or 4 lines, whatever. You may see something like this matching in your document. I talked about it and showed you the case in my earlier demo. So now we know this, that's the PI part. Okay, now comes the QI, right? Remember, we have to do PI times QI plus J. So how do we get the Q? Q is extremely simple. We take the ciphertext, we measure how many times each letter occurs in the ciphertext. That's how we measure the probability. Okay, so all we are doing here is essentially running this formula, right? This is the formula we are running. We start from j is equal to 0. We assume no shift happened. Let's reason about that. Why would that work? Let's say the plain text was never shifted, and somebody decided to use the key k to be 0, which means the shift is 0, right? Let's see why this algorithm will detect that. Okay, so we start with IC of y. Y is the ciphertext we want to break. Let's set j to be 0. In that case, what will happen? In that case, it will be PI times QI. Okay, and what is QI? QI means the ith letters probability. As I said, since the letters were not shifted because somebody decided to use the key to be 0, P of 0 will be same as Q of 0. P of 1 will be same as Q of 1. Therefore, this IC of y, when j is equal to 0, will give you 0.065. Okay. Now let's think about the scenario that j, the original key, was set to 5. Okay, How do we find out that mechanically in this process? All we are going to do now is we start from assuming j to be 0. Okay, that means we will be wrong, because what we are going to do is we consider the probability of we map a to a, b to b, and so on, right? By setting j to be 0, that's what you're doing. So we will be measuring the probability of a occurring in the ciphertext, b occurring, and so on, and multiply it with corresponding probabilities, which will be clearly wrong, because so let's say e occurred so many times on the ciphertext, but it was because somebody shifted using the key k equal to 5. Okay, but what we will be doing is we will be taking each letter and mapping it to a wrong corresponding letter. That's the reason why this won't work. So let me try to rephrase this, maybe more clear. Suppose maybe the k equal to 5 can be removed now. I'll just say this way, clarify it to you. Oh, undo, please. Oh, this is nice. I can do undo. Erase. Suppose I have my key, and I will be using, say, my key to be 23. Okay, I decided to use the key to be 23. Okay, and it's not clear to the attacker the key was 23. So how will this IC technique will find the key? It will start from character by character, right, from A through Z, and tries to map assuming J to be 0, meaning the key is 0. So when key is 0, A gets mapped to A, B gets mapped to B, and so on. Why would that not be 0.065? It wouldn't be, because the ciphertext that we are seeing here, right? Let's call this as a ciphertext mapping, right? And this is the plain text. We write all the letters of the plain text. We'll be mapping A to A, B to B. If we set the key currently to be 0 instead of 23, right? We set the J to be 0, and we are trying to brute force and try to find a good J. So what will happen in this case? We will be using, say, for example, E here, right? To E. We will be taking how many times A occurred in the plain text. We don't know that, but we will be using the English language approximation. And then we'll be measuring how many times A occurred in the ciphertext. Okay. It could be the case that A occurred so many times in the ciphertext. But what will happen now in that case? So we will be multiplying a small probability of A, because we know that let's assume EA and EAT occurs frequently. Let's say let's take some other example where one side has a very low occurrence, other side has a very large number of occurrence. Let's say we map. Yeah, we can live with this anyway. So we take a PI which may be very high in the plain text world, and the corresponding QI plus J may be very low because our J is incorrect. We didn't correctly guess it. Okay, so the probability of that will be small, because you're multiplying two fractions. One is smaller than the other one, which will not be equal to the 0.065 in the end. Okay, so by not having the correct mapping, our computation of IC of Y for different wrong J's will be off from 0.065. Off means really away from it, not just 1 or 2 decimals. It will be like 0.04, 0.03, and so on. Okay, therefore we will be able to clearly distinguish the plain text from other noisy plain text. Okay, that's the reason why this technique is able to work. So what will happen now is that what is E? E means P4, right, in terms of probability, because we start from 0, 1, 2, 3, and 4, and 5. A, B, C, D, E is 5th character, which means P4. We will be multiplying P4 with Q27, right? This is what we did here, because our K is 23. So what will happen now is we will be doing 23 plus 4 is 27, which is mod 26 is 1. Okay, so we'll multiply P4 with Q1. So what will happen in that case? In that case, we are not necessarily mapping the correct terms. Okay, if we map it correct, okay, so let's say our guess of the key k equal 23 was correct. E occurs so many times in the plain text. What is the corresponding E in the ciphertext? It will be B, right? Because Q1 means B. So we will be counting number of times E occurs in the ciphertext. I'm sorry, in the plain text through the English distribution, and the number of times B occurs in the ciphertext, which we know because we are given the Y, and we compute this. Okay, if our guess of the key k equal to 23 is correct, this sum of probability squares will be equal to overall 0.065, and we keep doing this for not only for P4, right? We have to do all the way from P0, of course. Where will P0 go? P0 goes to 23, whatever character 23 is, and P1 goes through 24, and so on. So we do this all the way to P25. P25 will be mapped to, where will it map to? 25 times 25 plus 23, which is 48, which is 22, right? So this is basically what you will compute for each guess. Only for the correct guess, the IC of J will be, for the correct J value, your IC of Y will be close to 0.065, and then you are done. Okay, that's basically what's the reason why the program was able to handle this automatically for us. Okay, so long story short, all we did was basically computed the index of coincidence on the ciphertext using the properties of the English language, the statistical properties. We did a frequency analysis essentially on large collection of texts and have the table, and then we used that to match up each plain text character probability with corresponding ciphertext character probability. We tried to sift by position 0 all the way to 25, one by one, until we get a hit where we saw the value of IC is greater than or equal to 0.064 or something like that. Okay, that's all. Thank you very much for your attention.